the product sigma algebra. Okay, so that the title of this section is product of major spaces. Product of sigma algebras, our first step in constructing product measures, is to construct the product of two sigma algebra. We begin with the following definition. Definition: rectangle. Suppose X and Y sets. A rectangle in X multiplied by Y is a set of the form A multiplied by B, where A is a subset of X and B is a subset of Y. Okay, if we product any subset of X to any subset of Y, we have a rectangle in this product space. Okay, for example, okay, for example, zero 1 multiplied by integer number is a rectangle in this product set. Or for example, 0 2 multiplied by radical 2 and 5, for example, okay, is a rectangle as a subset of this product space. This is a subset of X and this is a subset of Y. In this example, X and Y equal to numbers. Okay, we see the definition of rectangle in this figure. If A be any subset of X and B any subset of Y, this is a rectangle in X multiplied by Y. Okay, this is our rectangle. Okay, now we define the product of sigma algebras. Okay, product of two sigma algebras that we denoted by this. Suppose X and S and Y and 2 are measurable spaces, then the product S tensor T is the to be the smallest sigma algebra on this product that contain this set. These are all angles in X multiplied by Y. Okay, all rectangle. the smallest sigma algebra generated by this set. And a measurable rectangle in this sigma algebra is a set of the form R multiplied by B, where R belongs to S and B belongs to T. Okay. All rectangle such as this, where R belongs to S and B belongs to T, is called measurable rectangle. Okay. So that if we denoted if we denoted the sigma algebra generated by, for example, with SA, and we denoted already this notation for the sigma algebra generated by A. We know that this is the smallest sigma algebra that contain A. These two are equivalent. Okay. And this. And also we know that this equal to the section of all sigma algebras such as S. That S is a sigma algebra and A is a subset of S. Okay. So that this smallest sigma algebra or sigma algebra generated by A equal to this intersection of all sigma algebra that contain A, intersection of all sigma algebra that contain S. Okay. Now by this notation, if X and by the notation of both S, Y and 2, okay, and Y 2 R2 measurable space, measurable spaces, and A equal to the set of all measurable rectangle. Okay, A belong to S and B belong to 2. Then the product sigma algebra is so equal to SA. The smallest sigma algebra generated by this set. This is a subset of P of X, Y, okay? So that we can consider it as the definition of product of two sigma algebra, okay? The smallest algebra that contains these rectangles, measurable rectangles, okay? All of these are measurable rectangles. Please note that this set is not a sigma algebra in general, okay? For example, if we consider X and Y equal to R, then for example this is 0, 1, 2, 3, okay, in real line. Then see that, for example, this is a rectangle and this is a rectangle too, okay? This and this, okay? Rectangle 0, 1, 0, 1 and rectangle 3, 4 multiplied by 1, 2, okay? But the union of two rectangle is not a rectangle. We see that this union is not a rectangle. This union, by 3, 4 multiplied by 1, 2 is not a rectangle, okay? So that this set is not closed under finite or countable union. Even it is not closed under finite union. We know that any sigma algebra must be closed under countable union. Okay, this set is not sigma algebra, and we must form and construct the smallest sigma algebra that contains this set. This smallest sigma algebra is called product sigma algebra S tensor 2, for example. Okay. Okay. This product, so that this definition is very clear. S tensor T is S of A. I repeat again this for you. If we consider, for example, A equal to all measurable rectangles, okay? A belong to S and B belong to 2. Then this sigma algebra equal to the smallest sigma algebra that contain A, or by our symbol S of A, okay, S of this A. So that we know that any set is a subset of SA, okay? So that any measurable rectangle is in this product. Or briefly, for each A in S and for each B in tau, this product is a member of this sigma algebra. Okay, this is a member of this sigma algebra. Okay, and this is the smallest sigma algebra that contains all of these rectangles. Okay, dear students, do you have my voice? You don't have any problem? Okay, thank you. I say this for you. And we have the definition of cross sections of sets that we denoted by these and these. Okay, suppose X and Y are sets and E is a subset of this product. Then for each A in and B in Y, the cross sections EA, EB are defined by these sets. EA equal to this all Y that this order pair belong to E, and EB equal to this set. Okay, so that E is a subset of this product E is a subset of this product A, an element in X, and B is an element in Y. Then E A equals the set of all Y in Y. Please note that this is a subset of Y. Set of all Y in Y such that this order pay belong to E, and E be equal to the set of all X in X such that XB belong to E, so that this is a subset of Y and this is a subset of X. EA always is a subset of Y and EB is a subset of X. Okay, and we have these two important relations that we have these two important relations that Y is an element of EA if and only if R and Y belong to E. This is an element of EB. EB if and only if X and B belong to E. A direct consequence of these definitions. Okay, you use this relation frequently. Y is an element of this section if and only if A and Y belong to E and X belong to this section if and only if X and B belong to E. Okay, we can see definition of cross section in these two figures. For example, this is our subset of X multiplied by Y, and this is an element of X. Then this is this section. This is this section, the set of all Y in Y, because this must be a subset of Y. That A and y belong to E. Please note that if this is, for example, and y in this set, then this point A and y is an element of E, okay? The set of all y at this ordered pair belong to E. So that the first coordinate must be on A exactly, not any other points. And this figure, if we consider, for example, A in this situation, we see that for A1, for example, A1 equal to empty set, okay? Because this line an intersection by E, okay? This is empty set. And for ordinate, if we consider this E, for each B, this is EB, because any X in this set have these properties that, sorry, this, let me, okay. For example, this, okay? And this is X and B as a subset of E, okay? X and B. The second coordinate of all set in this line is B, okay? And we have this simple and useful example for each subset of X and each subset of Y, and any point in X and Y. The section of this rectangle, please note that in general this E is not a rectangle, okay? It is an arbitrary subset of this product. But if we consider rectangles, in rectangles the section in A equal to B exactly if A belong to A, and if are not belong in A, it is empty set. And this section for this rectangle equal to A if B belong to B, and otherwise this section equal to empty set. And it is very trivial because if we consider, for example, A as a subset of X, B a subset of Y, A an element in X, B an element of Y, then we see that this section of this rectangle have these properties that if we consider one element such as X or Y, for example, is an element of this section, this section if and only if A and Y belong to this product. This is told by this observation, okay? Y belong to this section if only if A and Y belong to E. Okay? This is our E. And this is hold if and only if A belong to A and Y belong to B. Both of these must be whole. Okay? Both of these must be whole. So that we have these two cases. If A belong to A, then this statement is whole, so that we must have this property and condition. And if A is not belonging, this is false, and so this statement is false. Okay? So that we can consider two cases. For example, case 1, A belong to A. In this case, we see that this equal to T, an always true statement, okay? And this is equal to Y belong to B. So that we see that this section equal to B. And in other case, if A not belong to A, we see that Y belong to this product equal to A and Y belong to this product, and we must have this statement again. But this statement is an always false statement. And this is an false statement. This is equal to Y belong to empty set. Okay, this is a false statement. So that in this case we see that these sections equal to empty set if A not belong to A. We don't have, in other words, if A not belong to A, we don't have any Y with this property. If this first coordinate not belong to A, we don't have any Y with this property, so that we don't have any Y with this property, so that this set must be empty set. Okay, this must be empty set. Okay, this T is a true statement and this C is a false statement. Okay, so that this section equal to exactly B when A belong to A and exactly empty set if A not belong to A. And similarly for this rectangle, this section equal to A belong to B and otherwise equal to empty set. The proof of this is very easy and similar to the previous. And we have this proposition. Suppose S is a sigma algebra on X and tau is a sigma algebra on Y. If E belongs to this sigma algebra, then the section of A belongs to tau for every A in X, and the section of E in respect to B belong to S for every B in Y. This is very nice because we see that the relation of this sigma algebra, product sigma algebra, with these two, tau and S, relation of this with each of these two sigma algebra. E belong to this sigma algebra, then these sections are in tau and S. Okay, and this is very nice. Let me write this again. Okay. E, if E belong to this product of sigma algebras, we have two statements for each A in X. This section belong to tau, and for each B in Y, this section must belong to S. Belong, we know that this is a subset of Y and this is a subset of X. Okay, and tau is a sigma algebra of subset of Y and this is a sigma algebra of subset of X. And for the proof, we see that if E denotes the collection of subset of E, subset E of this product, for which the conclusion of this result holds. If we consider E, for example, equal to the set of all E okay, at a subset of x multiplied by y, such that we have these two properties for each a in x. These sections belong to tau, and for each b in y, this section belong to s. Okay, then we see this E is a sigma algebra. We see two facts, 1 and 2. Please note 1 and 2. 1, E is a sigma algebra, and 2, this E contains or rectangles if A equal to the set of all rectangles, measurable rectangles, okay, A belong to S and B belong to tau. This set is a subset of this E. If we prove these two statements, we see that this sigma algebra must be a subset of E, because this sigma algebra, let me write it in right. Because this sigma algebra is the smallest sigma algebra that contain A. Okay, we know that this is the smallest sigma algebra containing A, and this is a sigma algebra containing A. This is the smallest and this is n sigma algebra, so that this must be a subset of this E, and this is our goal. This say that any element of this must be belong to E. Any element of E, so that any element of this sigma algebra must belong to E, so that any element of the algebra must have these two property and is complete, so that only we must prove these two conditions, and this condition is held by the observations, because if we consider this rectangle such instead of E, then this, we know that, let me add it some slide. Condition 2 is holds because if A belongs to S and B belongs to tau, then we have these two properties for each A in X. This section equal to empty set or B, and for each B in Y, this section equal to empty set or A by this. Okay. Or this observation. The section of rectangles equal to B empty set or I write okay, this is true, and this is equal empty set or A, empty set or A. Okay, and in each case these or these are in tau, and in this case empty set or A belong to S, so that for any rectangle we have these two properties, and in these rectangles are in E, so that it is important that we prove that E is a sigma algebra, and the proof is this is easy to the collection E is closed under complementation and countable unions becomes note that for the proof of 1, okay, at first we prove that E is closed under complementation okay, complementation. If E belong to E, then we must prove that its complement belong to E too. But we see that for each A in X, this section, the section of the complement, equal to, sorry, complement of E equal to y minus this section but E is an element of E, so that this section must be belong to tau, so that this complement must be belong to tau. Tau is a sigma algebra, and sigma algebras are closed under complementation, okay? And also for each B in Y, this section equal to X minus EB, and this is an element of S, because this is an element of S, so that its complement must be belong to S. And these two conditions lead to a complement must be belong to E, okay? E complement, so that this not X, this is X multiplied by Y, okay? We must write X multiplied by Y minus X multiplied by Y minus, and this E complement equal to this X multiplied by Y minus E, okay? Because E is a subset of X multiplied by Y. So that E is closed under complementation, and this equality is whole because if you consider, for example, an element of this set this is equal to A and Y must be belong to this set, okay? So that A and Y is not belong to E, and this is equal to Y is not belong to this section, not and not, okay? Because we have these properties, Y belong to if and only, so that this is not belong if and only if Y not belong to this section, okay? So that we have this, and so that Y must be belong to the complement of this set, complement of this set, complement of this section, okay? And similarly for this, X belong to this complement, this section of this complement, if and only if x to y belong to this set, and this is whole if and only if, so sorry, x and b, okay, so that x and b is not belong to E, and this is equal to y is not belong in this section, or equivalently, sorry, this is x not y. Okay, x not belong to this, so that x must belong to the complement of this set. So that we have these two equality, and this shows that for each A, this section must be belong to 2, and these sections must be belong to S. So that by definition of E, please note that we set E the set of all subset of this product such that for each A, this section belong, and for each B, this section belong to S. And the complement of E have these two properties, so that the complement of E must be belong to E, so that E is closed under complementation. Also, E is closed under countable union, because we have this equality. E is closed under countable unions, okay, because if we consider a countable member of A, then for each I in natural number we have these two properties. At first, for each A in X, AI A belong to 2, and 2 for each B in Y, AI B must be belong to S. But for this, I conclude that for each A in X union and this section that equals union, it is very easy. Must be belong to 2, and for each B in Y, the sections of this union, or equivalently, this union of sections must be belong to S, because all of these are in S, and S is a sigma algebra, and any sigma algebra is closed under countable union, so that this countable union must belong to S, and also this countable unions must belong to 2, because all of these are element in 2, and 2 is in sigma algebra, and this 2 says that this union must be belong to E. Okay, this union must be belong to E, so that E is closed under countable union and E is closed under complementation, so that we prove that E is a sigma algebra. And also we see that this sigma algebra contain are measurable rectangles, and since this sigma algebra is the smallest sigma algebra that contains this A, this must be a subset of E, and our proof is complete. And the proof of this is easy. That I want you prove this for itself. Please write the proof of this equality and this equality for itself. Okay, dear students, do you have any questions? Dear students, do you have any questions? Okay, Mr. Sajjad, thank you very much. Thank you for your attention, and goodbye for now. Goodbye.